All right, so we started to see the different relationships between the different properties that can describe a gas sample, so pressure, volume, temperature, and then N is the moles of gas, how much of that substance we have. And we're ultimately able to put all those pieces together to give us this combined gas law. So it shows us as we change, excuse me, as we change pressure, volume, or temperature, amount of gas, as we change one or all of those properties, how is the gas sample going to adjust? So we can solve for the secondary sort of characteristics for that sample as it begins to undergo complete those changes, I guess. And then we also saw the different laws we have. We can take those and basically do the same thing, but instead of showing how a gas sample is going to change, we can take that and create a single equation at the bottom here that's going to describe just an individual gas sample. So whereas the previous one, we had 1 and 2 on each side because it was showing how the volume, the volume is going to change. Same thing with temperature or moles of gas on the bottom. Now when we're looking at the ideal gas equation, PV equals nRT, now we're going to be looking at just describing one gas sample under a single set of conditions. So P and V are still pressure and volume, N and T are the moles of gas and temperature. But in order to completely relate those, we've got R, which is just the gas constant. And depending on what the value or the units we have for the other pieces there, the value for R can actually change. In this case, since we have pressure in atmospheres, volume in liters, the value for R is going to be 0.08206 liter atmospheres over mole Kelvin. But if we've got different units there, we're going to have a different value for that R, like I said. So we had cubic meters for the volume and Pascal for the pressure. We'd have 8.314, and then the unit you can see there. But what we're going to start to look at for the rest of this is just different practice problems using those two equations. So in some cases, we'll be using P1 V1 over T1 N1, or the ideal gas law. So with these ones, there's going to be, let me see, 1, 2, 3, 4, 5, 6, 7, 8. Looks like 8 different practice problems, and then we'll touch on density of gases, how we can kind of solve for that in the ideal gas law at the end of it as well. So we'll have like about 10 practice problems in total. So with these, I'd recommend you kind of working through them on your own. So you may want to pause the video, give yourself a little time to go through it, and then you can unpause it just to see if you get the correct answer. And if you wanted to, you could even kind of skip ahead to see the answer. And if you get the same thing, if you have the similar setup, you don't really have to watch the process of me working it out. But at least for the first few, that would probably be a useful exercise. But with questions like this, it's always useful to identify what information we have, what we're looking for. So in the question, the pressure in an aerosol can is 1 atmosphere and 25 Celsius. So that's going to be our P1 and T1. Assuming the gas inside obeys the ideal gas equation, what would the pressure be if the can were heated to 450 degrees? So we've got T2, and then we're looking for what would be the pressure. So we're looking for P2. So we've got pressure and temperature initially, temperature for the second set of conditions, and we're looking for the pressure. So we could use that entire combined law. So P1 V1 over T1 N1. But with this question, since we're not given any information about the volume of this container, the amount of gas, we have to just assume that it's going to be constant. So those don't actually matter, since the volume and the moles of gas are going to be constant. They're going to be the same on both sides of that combined equation. So we can effectively just remove them. And that's why when we go to solve this one, we'll be able to do P1 over T1, and then just have the same thing on the other side. And then the big thing with this one is just to remember that temperature needs to be in Kelvin. So for 450, that's really going to be plus 273.15. So that'll be 723.15 Kelvin. Oops, 7 didn't come out very well. And then with the initial temperature 25, so that'll just be 298.15 Kelvin. So the big thing with this one is just making sure we do have those temperature units in the correct unit, which is going to be Kelvin. But now we've got 3 of those 4 pieces. We can just plug them in, and then I'm not going to show the actual algebra for this one just because it's just going to be dividing 1.5 by 298.15, cross multiplying the 723. And you should get a pressure of 3.638, but with significant figures, we're going to round that to just 3.6 since we've just got 2 sig figs and all of our initial values there. And again, with this one, since we're not given information about the volume or the moles of gas, and if you just think about a can in general, it's going to stay the same size. And then the gas inside, as long as we're not releasing any of it, it's going to stay the same amount of gas. So that's why we can remove those from both sides of our equation here. And then with the second one, an inflated balloon has a volume of 6 liters. So again, I always like to just kind of indicate what each of these are going to represent. So that's going to be our V1. And with it doesn't really matter what we assign as 1 and 2, just as long as we keep those same pieces of information on the correct side. So I could call 6 liters V2 if I wanted to. I would then just have to indicate that the sea level pressure would be P2 in that case. But since I labeled it V1, that would make this P1. And then that balloon is allowed to ascend to an altitude until the pressure is 0.45 atmosphere. So that's going to be our P2. And then with the temperature during the ascent, it goes from 22 degrees C. So I'll do it over here since we're going to have it in Kelvin anyway. T1 is going to be 273 plus 22. So that'll be 295.15. T2 is going to be that negative 21. So the negative sign just got kind of displaced there. It's on the top line where the number's on the bottom. But it'd be 273.15 minus 21. So that'll be 252.15. And in this case, we're given pressure, we're given volume, we're given temperature. So we got to assume that the moles of that gas is going to stay constant within the balloon. So we don't have to worry about N in this case. And we'd be able to just do P1 V1 over T1 is equal to P2 V2 over T2. Because we've got both of the pressures, we've got both of the temperatures. The only piece we're missing is going to be that second volume. So that's going to be what we'll solve for. We'll plug everything into the left, do that multiplication and division, cross multiply by the temperature on the bottom. So you could do 1 times 6 over here, divide by 295.15, cross multiply by 252.15, and then divide by the that new pressure, the 0.45, and that's going to give you a V2 of, I have it written down, 11.39. And that'll be in liters since that's what our other volume's in. But since we've only got 2 sig figs in all of these, we're going to want 2 sig figs as well. So we'll round that from 11.39 just to 11 liters. And then we're just going to continue with 5 more of these, I think. Some of them will have the ideal gas law rather than the combined gas law. But a balloon is inflated with helium to a volume of 45 liters. So that'll be V1 at room temperature. So T1. And again, that has to be Kelvin. So that'll be 298.15 instead of 25 degrees Celsius. But if the balloon was inflated to the same amount of helium on a very cold day, negative 10 degrees, T2, what is the new volume? So again, we can eliminate the pieces of information that are going to be constant. That's going to be the pressure. Of course, on a cold day, we may have different air pressure, but for this question, we don't have any information about that pressure. So we're just going to assume it's going to be the same in both cases. And in which case we can just remove it from our equation because it's going to cancel itself out. Same thing with the moles of gas. In this case, we're not told exactly how much it is, but we're told to see the same quantity of helium. So the moles is going to cancel on both sides as well. We'll just have V volume over temperature. And again, the big piece with this, the easiest way to kind of mess this up is to include negative or include degrees Celsius, so -10 for one of them, 25 for the other. But we would just want to convert those to Kelvin. And then ultimately, we would solve for V2 and see that we're going to get a volume of a little bit over 39 liters. But with sig figs, that'll be exactly what we rounded to. So since we only had 2 sig figs in that first volume, we can only have 2 sig figs in our second volume. And that's why we're going to have 39 rather than 39 point, whatever the calculator is going to give us for those remaining digits. Okay, so a similar one. In this case, we're filling a balloon with hydrogen. So typically, we wouldn't do that unless we were probably going to use it as some sort of ignition, because remember, hydrogen is going to be flammable, whereas helium is a noble gas, so it's going to be essentially unreactive. That's why helium's used in blimps and things like that now. But we take that helium and fill a balloon to 1.35 atmospheres, and that brings it to a volume of just over 2.5 liters. And then while the temperature is constant, we're going to increase the pressure. We want to determine what the new volume is going to be. So we've got, what is it, P1, and then V1, P2. We're looking for V2 then. And then with this one, we're not going to be dividing, so we'll have P1, V1 is equal to P2, V2, where we're solving for V2. So we'll do 1.35 atmospheres times 2.54 liters on the left, divide by the 2.5 atmospheres on the right, and that'll give us our new volume for that hydrogen balloon. And what we're going to see is it's going to be 1.37 liters. And then with these ones, again, we have 1.37 just because the sig figs there, all those values have 3 to begin with. But with this one, always just kind of double check yourself, see if that answer makes sense in terms of what you're plugging in here. Because in this case, we're multiplying. So when we increase the pressure, 1.35 to 2.5 atmospheres, we're going to have to decrease the volume then. So it makes sense that the volume goes down. Remember, pressure and volume are going to be inverse. But also, if we look at the numbers here, on one side, we've got 2.5 even. On the other side, we've got 2.54. So on the side where we've got 2.54, we are also multiplying by 1.35. So since we've got a slightly larger number than 2.5, that means on the opposite side, we're going to need a number that's slightly larger than 1.35. So 1.37 at least makes sense. All right, and then in this case, for this next one, a sample of oxygen gas is at 0.5 atmosphere and occupies a volume of 11.2 liters at 0 degrees Celsius. What will the gas occupy at 6 atmospheres at room temperature, which they're going to assign as 25 degrees C? Little hot there. I think room temperature is usually around actually like 21 or so. But for this one, we're given the initial pressure, so P1, V1, and then T1. And then in the second piece of it, we're given T2 and P2. So we want to find V2. So when we plug it in, we'll have P1, V1 over T1. And then do the same thing on the opposite side there. But again, just remember, with these temperatures, we got to change them to Kelvin. So we'll have 298.15. T1 will be 273.15 since it's just 0 degrees Celsius. And then when we plug all those in and just rearrange it to solve for the, not pressure, we're solving for the second volume. What we're going to see in that case is we'll wind up with a volume of just over 1 liter. And then with sig figs, we'll round it to 1.02 liters there. And then again, I'm just not showing the actual algebra just because it is kind of a hassle to write with this stylus. and then keep everything sort of legible on here. But with it, once we assign those different pieces, identify what information we have, what we're looking for, we're just going to be doing the algebra. So in this case, we'd have 0.5 times 11.5 or 11.2 liters on the top on the left side, divided by 273.15. We can then cross multiply by the second temperature, 298.15, and then we'll divide it by that 6 atmospheres to get V2 by itself there. Okay. And then in this case, we've got a sample of carbon dioxide now, and it gives us the pressure in millimeters of mercury, so 125 millimeters of mercury, with a volume of 2.5 or 250 milliliters, excuse me. This sample is moved to a different flask now, and the resulting pressure is going to be 189 millimeters of mercury. We want to figure out what the volume of the new flask is going to be. And then for this one, we're assuming temperature is constant. In this case, it's given, that's told explicitly. But even if we didn't have that sentence in parentheses, we'd have to assume that. Otherwise, there's not enough information to actually solve for this one. Because if we're changing the volume of the flask and then we're also changing the temperature, those are both going to influence the pressure. So we would actually need that information explicit. So if it's not given, we just got to assume that that's going to be constant. Doesn't actually matter what it's going to be. We're just going to assume that it's constant. So in this case, we've got P1 and V1. We've got P2 for that 189 millimeters of mercury. And then this is the first time we've seen that unit in these questions. So up until this point, it's been atmospheres. But with the P1, V1 equation, that combined gas law, temperature and moles on the bottom, the units we're plugging in aren't going to be important as long as we have the same thing on both sides. So in this case, since we've got millimeters of mercury for both of those pressures, those units are just going to cancel. So we don't have to worry about converting those at all. Same thing with the volume, it's in milliliters. That's fine, it just means our answer is going to be in milliliters. So with this one, we've got P1, V1 is equal to P2, V2. And then again, we've got 3 of those pieces, just missing that final one, the V2. And when we go plug them in, do 125 millimeters of mercury times 250 milliliters, divided by 189 milliliters of mercury, what we're going to get with our significant figures. So we want 3 sig figs, since all of those values have 3, because that 250 has the decimal afterwards, so that signifies that that 0 is also significant. If we didn't have that decimal, we would only have 2 there, so we'd round our answer a little bit differently. But in this case, since we've got 3, we're going to have a new volume of 165 milliliters there. All right. And then with this one, we're actually going to start using the ideal gas law. So PV equals nRT. Excuse me. And the reason we're going to be doing that now is because we've only got one set of conditions. So in this question, if we take calcium carbonate, often just used in antacids and things like that, it's going to be a base, so it neutralizes the excess stomach acid. But if we heat that substance, it's going to decompose into solid calcium oxide and then just carbon dioxide gas. And then with this question, a sample of that substance is subjected to heat, and then the resulting carbon dioxide that's produced is collected in a 250 milliliter flask. When the reaction is complete, when that decomposition is complete, the carbon dioxide now has a pressure of 1.3 atmospheres and a temperature of 31 degrees Celsius in that flask. We want to figure out how many moles of carbon dioxide were generated. So in this case, we're not seeing a gas sample change from P1 to P2 or anything like that. We're just trying to figure out how many moles are in this single sample under these specific set of conditions. And that's why we're going to be using the ideal gas law, PV equals nRT. And then with R, remember, there's going to be a whole bunch of different values we could have for that based on the units. But since we've got liter, atmospheres, moles, and Kelvin, what we're going to see is we'll have 0.08206. And then the units there, liter, atmosphere on top, mole, Kelvin on the bottom. So if we look at just where we're plugging that in, plug it in on the right-hand side. N is going to be moles. Temperature is going to be in Kelvin, so we'll have to change that 31 degrees C. But moles and temperature will cancel the bottom of that R unit. And then since we've just got liters and atmospheres on the other side, that's why we just see the units we have here. But this is just going to be an experimentally determined constant. But with this one, there's a couple things we'll have to change. So we'll have to change the temperature to Kelvin, so add 273.15. And then also with the volume, 250 milliliters, we'll want to make sure to convert that to 0.25 liters, because with our value, again, we've got liters in it for the units there, so we need the volume to match that. We could adjust the R constant and move the decimal over and have the same thing, but it's just a little bit more tricky to do it with the R rather than just changing the volume unit. But with this one, we want to solve for N, so we'll rearrange it. Divide by RT on both sides. So when we go to plug it in, we'll have pressure, which is going to be 1.3 atmospheres. Volume, remember, change to liters to match R, so 0.205 liters. And then I'm just going to put R rather than writing out that entire thing. But then with the temperature, won't be 31. It'll be 31 plus 273, so we can get it to Kelvin. So that's going to be 304 and change, so 304.15. And then when we go and actually solve for that, we've only got 2 sig figs in these values given. So 250 milliliters only has 2, 1.3 and 31 also only have 2. So we'll only want 2 in our final value. So that means we'll round it to 0.013. Again, that will be moles since we're solving for N there. All right, and if we look at one more with the ideal gas law before we start to look at how we can manipulate that ideal gas law to look at density of gases. In this case, we won't be solving for moles, we'll be solving for pressure. So when we rearrange PV equals nRT, we'll still have pressure on the left, nRT on the right, but now we'll be dividing it by that volume. So we'll have V on the bottom there. So when we go to plug it in, 1.2 moles of this substance, so methane, but it doesn't actually matter for these gases what substance it is, at least for this type of calculation. And then again, I'm just going to do R rather than writing out 0.08206. Temperature, still got to convert it to Kelvin, so 298.15 instead of 25, and then we'll have 3.3 liters here. So when we actually solve for this one, 2 sig figs again, we're going to have a pressure of just under 9 atmospheres, so 8.9 there. All right, but with the ideal gas law, like I mentioned at the very start of this, we can rearrange this and kind of manipulate it to look at the density of the gases. So if we just take our original equation, PV equals nRT, and divide each side by volume, as well as the gas constant times temperature, we see the equation rearranged like we have now. So I can rewrite it. So PV equals nRT, and what we're simply doing is just dividing both sides by volume, dividing both sides by RT. So the reason we see it like we have is kind of just actually flipped the way I have it, is volume is going to cancel. Oops, and I forgot to do it on both sides. So we'll still have RT on this side, on the bottom V there, but R and T will cancel. So we'll wind up with pressure over gas constant times temperature, moles over volume. And then we can further kind of manipulate this by thinking about what moles is. So moles is going to be the molar mass, or the mass of that sample divided by the molar mass, or the molecular mass as it says here. So we can rearrange that. And with it. So moles is equal to mass over molar mass. So if we plug in this for N, and then just multiply by the molar mass, so we get molar mass on the top here. On the left-hand side of our equation, now we've got mass over volume. So now we're going to be able to solve for the density of a gas using this equation. And then we could also just plug in D. So instead of M over V, we could actually just plug in density now on the left-hand side. And then along with that, if we know the density of a gas sample, we can rearrange this to solve for the molar mass or the molecular mass of that substance. So it's kind of the exact same equation, just depending on what piece we're actually solving for. But we'll be able to look at a couple examples for each, or for one of, or each of those rather. So the first one, what is the density of carbon tetrachloride vapor at 714 torr and 125 Celsius? So the first thing I'm going to do is just convert these to atmospheres in Kelvin. So with torr, 760 torr is equal to 1 atmosphere. So since we're less than 760, we should have less than 1 atmosphere. And when we convert this, we'll get 0.939 atmospheres. And then 125 will just be 398. Whoops. Okay. So if we think about the equation we just saw, if we're solving for density, what that means is we will have the pressure times the molar mass, PM, over RT. And in this equation now, we've got the pressure. So we've got P. On the bottom, we always have R, just a constant. We've got temperature. So the only thing we're missing is that molar mass. But since we're given the name of the substance, carbon tetrachloride is going to be 1 carbon with 4 chlorine. We can get the molar mass, which is going to be 153.81 grams per mole. And with the molar mass, the reason the units on that are going to be important is because we'll be able to cancel moles. And then in the gas constant, we'll have the units canceled for everything but the volume, which is going to be in liters. So depending on what units we have for that molar mass, that'll determine what units we actually have for the density. So in this case, since we've got grams, our density is going to wind up being in grams per liter. Because again, that R constant has liters as the volume unit. But if we converted this molar mass to 0.15381 kilograms per mole, then we would have kilograms per liter in our density value. But now we've got all of those pieces, we can just plug them in. And when you do that, you'll have 0.939 torr, or 0.939 atmosphere, excuse me, because we converted from torr, times 153.81 grams. We'll divide by the gas constant, we'll divide by 398.15 Kelvin. And what we're going to see is we'll have a density of 4.42. And then again, it's going to be grams per liter because that's the unit we had on our molar mass. So if we think about the units for a second, on top we'll have atmosphere. And then grams per mole. On the bottom, we'll have liter atmosphere over mole Kelvin. And then we'll have Kelvin. So if we just go through it again, look at the units here. Kelvin's going to cancel. Mole on the bottom of our molar mass, and then mole on the bottom of the gas constant. Since that fraction on the bottom, we're essentially just going to kind of reverse it. Dividing by a fraction is the same as multiplying by the inverse. So we can really think of this as grams per mole times mole Kelvin over liter atmosphere. So we'll actually see mole cancel. Atmosphere is going to cancel. So the only thing left now is grams on top. Again, liters is going to wind up on the bottom because that's going to be the inverse of that fraction ultimately. So we'll wind up with grams per liter. But again, if we plugged in 0.15381 kilograms per mole, then that would change the unit on our density there. All right. And then with the final one we're looking at, it's going to be a fairly complicated one. It's still going to be using that same ideal gas law with density in there. But in this case, we're going to be solving for the molar mass. And we'll have to do a couple other pieces with it. So if we just read through the question at first, a series of measurements are made to determine the molar mass of an unknown gas. First, a large flask is evacuated and found to weigh 134.56 grams. So evacuated just removes, it was purged of everything inside of it, so that mass is strictly just the flask itself. And then the flask is filled with gas to a pressure of 735 torr at 31 degrees Celsius. And then the mass is determined with the gas in there to be 137.456 grams. And then after that, the flask is completely filled with water at the same temperature and found to weigh 1,067.9 grams. We're given the density of water. And again, we want to figure out the molar mass of that unknown gas. So we're still going to be able to use, so molar mass is going to be equal to density, so the RT over P. But we're not given really anything directly other than the pressure. And R, I guess, so we always have R. So we've got this one, we've got pressure. We can get temperature fairly easily just by adding 273.15 to do the temperature, but the density is going to be a little bit tricky. But if we look at what we have to start, we need, for the density, we need the mass of the gas divided by the volume of the gas. So with the math, we could just do 137 point whatever minus 134 point whatever, and that'll give us the mass. But for the volume, we're going to have to focus on the water. And with that one, clear this. So with that, if we think about now the volume of the flask, oops, not density, or not mass rather. So volume is going to be mass over density. With this, we can look at the water because we've already got the density. So we've already got that bottom piece, 0.997 grams per mole, per milliliter, excuse me. And then with the mass on top, we've got the initial empty flask, 134.567. We've got the mass of the flask filled with water, 1,067.9. So if we subtract those two, we can get the mass of the water. So we can ultimately solve for the volume. And then the volume is going to be the same, whether it's filled with water or it's filled with gas. And again, we already calculated the mass of the gas, so we can go through and solve for these pieces. So just to see how we kind of do this first, we'll get the volume of the flask by doing mass of H2O divided by density of H2O. And what that's going to give us is 1,067.9 grams minus 134.567 grams, and then again divided by the density, 0.997 grams per milliliter. So again, when we divide by a fraction, same as multiplying by the inverse. So it's really flipping that unit to milliliters over gram. So grams are going to cancel since we've got grams on the top, grams on the bottom, and then milliliters will be left as our final unit. So we're going to see the volume of that flask with significant figures will be 936 milliliters. But with it, when we go to plug it into our ideal gas law, we'll have the gas constant in liters. So I'm just going to go ahead and multiply this by 1,000, or divide by 1,000, excuse me, since we're going milliliters to liters, and make it 0.936 liters. And then again, we were already given the temperature. We just have to convert it to Kelvin by adding 273.15. We can get the mass of the, I guess the temperature is getting ahead of itself. But we can get the density of water, or the gas rather, because now we had the mass of the flask filled with gas, 137.456 grams, minus the empty flask, 134.567. Divide by 936 liters, 0.936 liters, excuse me. And the density of the gas then is going to be 3.09 grams per liter. So now we've got the density. And then if we go back, we have the pressure, 735 torr. We can convert that to atmospheres just by dividing by 760. So we're going to see that pressure is really going to be 0.967 atmospheres. So we've got the pressure, temperature. We can just add 273.15 to R we already have. So when you plug all of that in, what we're going to get is a number pretty close to 80. But since we've only got 2 sig figs in the temperature, we only want 2 sig figs in our final measurement. So we're going to wind up with 80 even, because we'll put the decimal after that 0 there to show that that's also significant. Okay. And then with the next section of this, we'll start to look at how we can use chemical equations to do stoichiometry related to gases, reactions that contain gases.